25-degree weather for at least a couple of days. Always welcome this time of year. So I'll be giving 3 lectures. This is the first of 3 lectures on the general topic of quantum optomechanics and quantum measurements. And so for any of you who have looked at the program, you'll see that quantum optomechanics at this school is well represented. I think I'm the first of 5 people who will be touching on quantum optomechanics. And as I'm the first person addressing this topic, I'll really try to introduce you to the basics. And so in this very first lecture, what I really hope to sort of cover are the basics of quantum optomechanics theory. And in lectures 2 and 3, again, we'll see how the timing works out, move on to talking about sort of quantum measurement with these systems, and even some more interesting kind of quantum measurement things you can do. In this first lecture, which I guess is over here, the things I'll really focus on are a kind of simple regime of quantum optomechanics, the so-called linearized regime of quantum optomechanics. So full disclosure, the next hour will be spent talking about a quadratic Hamiltonian, and I will show you can still do interesting things with a completely quadratic Hamiltonian. And a lot of the things that I'll be telling you about are things that, in a sense, are almost taken for granted in this community. So hopefully, having listened to this talk, the next time you hear a seminar on quantum optomechanics, the at least first 5 or 10 minutes will make sense. So great, let's launch right into it. So quantum optomechanics, what's the basic idea? There's an ever-growing community that is interested in systems where photons in a cavity, maybe an optical cavity, maybe a microwave cavity, are interacting with some kind of large mechanical degree of freedom. And all I mean by large here is much bigger than a single atom or a single ion. And there's a huge diversity of systems that people are looking at. The amazing thing is that almost all the systems, the basic physics can be reduced to this little cartoon. So what do we have in this cartoon? We have a driven Fabry-Perot cavity, and I'm going to focus on just one resonant mode of that cavity. And we have one mirror that can actually move. That's the mechanical degree of freedom. So what's the most basic thing that we can get from this cartoon? Well, look, as that mirror moves, the length of the cavity changes, the frequency of the cavity is going to change. So the frequency of this cavity depends on the position of the mirror. That's going to give us a way to make a sensitive measurement. So as the mirror moves, the frequency of the cavity is changing. If I'm driving this cavity with laser light, that means the phase shift of the reflected light will depend on the mechanical position. Okay, so one of the many reasons people are interested in these systems really give you a way of making incredibly sensitive position measurements. And in fact, they can really approach the quantum limit on how well you can make a continuous position measurement. And that's something I'll really spend time talking about and defining carefully in the second lecture. So the other aspect, a very basic aspect of these systems, will look, if you can make a good measurement of position, and you can do that near fundamental quantum limits, well then the physics of back action must be important. If I'm measuring position, momentum doesn't commute with position, momentum must be messed up. So in this system here, what is the back action? How is the mirror influenced by the measurement? It's basically radiation pressure forces. So the photon number in the cavity is going to act as a fluctuating force on the mirror. Okay, and that isn't just a bad thing, these back action forces. This is a good thing. The forces exerted by the photons in the cavity will actually give us a way to control what the mirror's motion is doing. And one of the biggest applications of that we will address in this first lecture is the physics of back action cooling. You can actually use these radiation pressure forces to cool this kind of large mechanical degree of freedom, in principle, all the way down to its quantum ground state. Okay? So again, the lectures I'll be giving will really focus on the theory of these systems, and again, I think following me will be a number of experimentalists giving you more experimental details. It's still nice just to really look at some pictures to get a sense of the immense diversity of this area. So shown here on the right is something taken from a, I guess, fairly old now by the standards of this field, review from Tobias Kippenberg and Kari Vahala, just showing you the kind of range of systems that really realize the simple physics in this schematic here. So this physics is realized in the kind of interferometers that are used for gravity wave detection, where the masses that are, this end mirror that's moving are in the kilogram regime. The resonant frequency of the mechanics is tens of hertz, going all the way down to realizing this kind of Fabry-Perot cavity by gluing a mirror onto an AFM, an atomic force microscopy cantilever, to these kind of optical microtoroid systems, where now the mechanical frequencies are getting up into the megahertz regime, the masses are in the nanogram to picogram regime. You can even realize this physics without using optical photons. You can realize it in a circuit. Okay, and this is something we'll hear a lot about in John Teufel's lectures later in the week. So instead of having an optical cavity, you could have a LC circuit, let's say made of superconducting aluminum, and instead of having a movable mirror, how will I have the cavity frequency depend on X? Well, imagine I exert my PowerPoint skills and I make the capacitor vibrate like that. Okay, well, with a little bit more work, you can actually build a system that realizes this physics. You have exactly the same basic physics, but now it's microwave photons in this circuit basically interacting with the vibrations of this drumhead mode of this capacitor. And again, John will no doubt tell you about this in more detail, but one of the really kind of amazing recent results that come out on a system like this is to really cool the motion of this kind of drumhead mode of this, I don't know, maybe it's 15 microns in diameter capacitor plate at 10 megahertz mechanical resonator, almost all the way down to the quantum ground state. So having a number of phonons that's on the order of a third. Okay? So the diversity doesn't stop there. Other kinds of systems that people are really excited about in this field, you can start playing games with so-called nanophotonic systems. So there's this amazing class of systems really developed in Oscar Painter's group at Caltech, so-called optomechanical crystals, where you take a beam of silicon, you pattern it with holes, and now you get both localized vibrational modes, that's the mechanical resonator, and also using kind of the physics of photonic bandgap materials, you get localized optical modes. And so the amazing things about these patterned beams, you can essentially have many, many coupled optomechanical cavities on this single system. So another interesting class of systems, another class of systems where again you realize this physics that again will be represented at this school, is to play these same games now with cold atoms in a cavity. And we'll hear about this from Dan Stamper-Kern, who's talking later in the week. And the idea in this system, so again, you have a bunch of atoms in a cavity. How does that resemble this cartoon here? It's the collective motion of that cloud of atoms, the cold atoms in the cavity, that acts like the mechanical degree of freedom. And again, the same basic physics, as that atomic cloud moves, it changes the frequency of the cavity. That's basically what we need to play these games of quantum optomechanics. Okay, so lots and lots of different systems. Amazingly, the basic physics reduces to something that's easy to sketch on the slide. Let's start to try to understand some of the physics of these systems in a little bit of more quantitative detail. So of course, the first thing we have to do is what is the Hamiltonian for these systems? And let's start in the absence of any kind of dissipation whatsoever. So what do we have? And here again is this Fabry-Perot cavity where I have a movable end mirror, and this drawing here stuck on this beam. Well, the basic thing we have is there's a mode of the optical cavity that we're interested in. That's just a harmonic oscillator we heard about in the last two lectures. The photon lowering operator is A. And we have a mechanical resonator. We're going to focus on one vibrational mode of this beam. That's also a simple harmonic oscillator. Its position is X. I can write that in terms of phonon raising and lowering operators. I'm going to call that B. Okay, so that's the two modes of interest. How do they interact with one another? Well, again, the basic physics is as the beam moves, it changes the frequency of the cavity. So this cavity frequency is dependent on X. In almost all the systems that people are looking at, relatively speaking, the displacements that we're interested in are small. So I can just tailor expand that dependence. So the cavity frequency, to a good approximation, is just modulated in a linear way by the mechanical position. And boom, I have my basic cavity optomechanics Hamiltonian. So it's just as simple as having two harmonic oscillators, photons, phonons, and then this interaction here, where again, it's just coming from the fact that the cavity frequency has a linear dependence on position. Okay, when I write things out now, in terms of using the 0-point motion of the oscillator, I get this fundamental single photon optomechanical coupling constant, little g. Okay, and again, in typical experiments, how big is this little g? You know, anywhere from just a few hertz to, if you're really doing well, maybe a fraction of a megahertz. Okay, so as innocuous as this Hamiltonian looks, this is not a quadratic Hamiltonian. This Hamiltonian has some real nonlinearity. There are products of 3 raising and lowering operators there, and that's going to be the source of a lot of interesting physics. Okay, and again, just to really emphasize the basic physics that I already mentioned, just from this coupling term, A dagger A multiplies X. That means the mechanical resonator controls the frequency of the cavity. And also from the mechanics point of view, right, anything that multiplies X in the Hamiltonian is a force. Right? So as far as the mechanical resonator is concerned, the number of photons in the cavity are a force that's pushing it. And that's just radiation pressure. And I should also say, again, it's a nice, relatively small group here. If there are questions or things that don't make sense, definitely stop and ask. Okay, so that was all without dissipation whatsoever, but with no dissipation, this would not be a very interesting system. So we have to add some dissipation. We have to open up our system to the rest of the universe. So let's start with just the cavity side of things. And again, this is stuff that was already described in Steve's talks. And so for the cavity mode, we're going to make this mirror here not fully reflective, so photons can enter and leave the cavity. The way that we'll describe that coupling between the mode of interest in the cavity and all the photons outside of the cavity is just as a coupling to a bath of bosons. Those bosons, B sub q, think of them as the photon modes outside of the cavity. So here are all the photons outside of the cavity. Here's this very simple coupling that basically says a photon in my cavity could tunnel out of the cavity or back in. And again, the fact that I can get away with such a simple coupling here, I'm really going to use the fact that we're interested in very, very, small, high-quality factor cavities. So the damping rate, the transparency of this mirror is going to be very, very, very small. This photon tunneling is going to be very, very weak. A lot of the details of the photon modes outside of the cavity just aren't going to matter. So all that's going to show up here, rho here is the density of states of these photons outside of the cavity. And this coupling constant, right, the thing that's this tunneling term is proportional to square root of kappa, that's going to be the damping rate of the cavity. Okay, so now if you play the same games that Steve told us about in terms of deriving the Heisenberg equations of motion for this system, what do you get for the Heisenberg equation of motion for my photon operator? Well, there's the coherent term that just comes from these two terms in the Hamiltonian, that's this commutator here, and then the coupling to the to the dissipative terms, the coupling to the modes outside of the cavity, well, they'll give me a damping term, so the photons can leak out of the cavity, and they'll also give me these driving terms. Okay, and this driving term I've split into sort of 2 different pieces. Well, if I'm actually driving the cavity with the laser, right, I can think of these bath modes, the modes outside of my cavity, as having an average value. So that's what this A bar in represents. Really think of that as the amplitude of the laser light that's driving this mode. And again, that term there, that's exactly what you would get if you just stuck explicitly a driving term in the Hamiltonian. Right? That's the way I would put in a driving force to drive this cavity harmonic oscillator A. So that's the driving term. The stuff that's left over, the A hat in, that's going to represent noise that actually enters the cavity through this partially transparent mirror. Okay, so that's the basic way we're going to describe dissipation here in terms of this kind of quantum Langevin equation. We can basically do exactly the same thing to describe the mechanical resonator. And again, the key idea is if our mechanical resonator and our cavity are sufficiently high quality, if their damping is sufficiently weak, all the details of what is it that exactly damps these two systems isn't going to be so important. These simple kind of Langevin equations are going to do a good job in describing the physics. Okay, so we have our coupling. Yep.
What's the A bar?
A bar here is really meant to represent the amplitude of the laser drive applied to the cavity part. So that's something we can tune in the experiment.
Is it classical?
Yeah, so here this is not an operator. So I'm really thinking of my laser in terms of a coherent state. It has some amplitude, which is just a complex number. And that complex number is really showing up here as telling me about the amplitude of my driving force. Okay, so again, just try to keep things nice and basic to begin with. In terms of, so we've got our cavity optomechanics Hamiltonian, we've got the coupling to the dissipation. It's standard to make some transformations to make this Hamiltonian look a little bit nicer. So the first thing to do is to go into a rotating frame. So look, I'm driving this system with some laser light, and so that laser amplitude is going to be time dependent. Omega L here is the laser frequency. And I've parameterized the amplitude of that laser drive by this parameter alpha L. So it's very convenient to go into a rotating frame where we basically get rid of this time dependence. Okay, and the way we do that is a unitary transformation that basically, if I think of this driving Hamiltonian here, I want this A dagger to pick up a time dependence that perfectly kills the time dependence of the laser drive. So we know how to do that. It's this unitary transformation here. It just involves an A dagger A in the exponential. And again, the one little tricky thing is when I make a time-dependent unitary transformation, what's the new Hamiltonian? Well, here's the piece we all know and love. But because U is time-dependent, there's an extra piece that comes in. And that extra piece here is very simple in this case. That extra piece, all it does is shift the cavity frequency of this Hamiltonian. So when we go into this rotating frame, a frame in which this laser drive is effectively now time independent, our coherent Hamiltonian, the frequency of the cavity now isn't the bare frequency omega cavity, it's this detuning parameter delta. It's the way I define delta throughout this talk. It's the laser frequency minus the cavity frequency. Okay, so that's going into a rotating frame. One thing we do to make the Hamiltonian simpler. The other thing we do is we want to separate out the interesting part of this photon lowering operator A from the kind of boring classical part. So the way we're going to do that is, in a sense, make another unitary transformation, a displacement transformation. So here's that equation of motion that I wrote before for the photon lowering operator for my cavity. So now we're in the rotating frame, so the frequency now is this delta, this detuning parameter. And here is my laser drive, which is not time dependent in this frame. And so if I ignore, this term here represents the noise, coming in with that laser drive. If I ignore that completely, that's an equation we can all solve, and that's basically solving for the average value of A. That's going to give me the average amplitude of the field inside the cavity. Okay, so that's something that's there, that has nothing to do with the optomechanical interaction, doesn't know about the noise. It's very, very convenient to basically shift that out of our operator A. So what I'm going to do is define a new operator, D hat, which is also a canonical bosonic lowering operator, just by writing A as this, if you want, boring classical piece that's completely set by the laser frequency. And everything that's left over goes into this operator D. And also, just to make things convenient, I'm going to put a phase factor up front here, e to the I phi alpha. That's exactly the same phase as this classical amplitude alpha. Okay, so when I make this transformation, if I ask what's the average value of D, well, the average value of this new operator D is going to be 0. Okay, so this is known as making a displacement transformation. It's also common to refer to this operator D as the quantum part of the cavity field. So what's going to tell this operator D what to do? Well, it's not this external laser drive. It's going to be the noise in the system, and it's going to be this optomechanical interaction. Okay, so we do that, and again, it's really just as simple as everywhere in the Hamiltonian, I had an A, I replace it by alpha plus D. What does our interaction now look like? Well, then here again is our interaction constant little g. Here's the mechanical position. Here now is the photon number in the cavity in this displaced picture. And again, alpha is just a complex number, okay, the classical cavity amplitude. So this first term, this is just a constant multiplying x. More or less, that's a kind of boring term. That's just going to shift the equilibrium position of the mechanics. We don't really need to worry about it. Well, maybe we should. We'll come back to that a little bit. That looks pretty innocuous. We see that now in this displaced frame, we get a kind of linear interaction, right? A term that involves 1 alpha and d plus d dagger. And then we have a term that involves, again, the full nonlinearity d dagger d multiplying position. Okay? So what am I going to do? Well, look, we have this wonderful nonlinear Hamiltonian. I'm going to do things that's going to make life very, very easy, right? I'm going to come up with a reason to drop the nasty nonlinear term. Okay, and the reason I'm going to come up with is experimental reality. Experimental reality is that constant little g is usually incredibly small. So I said order of magnitude a few hertz to maybe, if you're lucky, a fraction of a megahertz. What should we compare that against? Well, how strong is this interaction compared to the damping rate? How quickly do photons leak out of the cavity? So that typically is on the order of a fraction of a megahertz or bigger. So the idea is that this little g all by itself is really small in most experiments compared to the dissipative rates for the cavity. So this term by itself is not going to do a whole lot. But this term here, right, this term that we get by driving my cavity going into this displaced frame, this interaction term between photons and phonons is enhanced by the average amplitude in the cavity. So by strongly driving the cavity, I can make alpha pretty big, right? If I have a lot of photons on average in the cavity. So g times the magnitude of alpha, that might actually be significant. Okay, so we're going to work in this regime where you need to have a lot of photons in the cavity on average to have any kind of useful optomechanical interaction. What that means is we're just going to completely neglect this term. Okay, and so what we're left with is an interaction that has this very simple kind of quadratic form. And we're now going to introduce a new interaction constant, the so-called many-photon optomechanical interaction, big G, which is this original interaction, little g, times the square root of the average number of photons in the cavity. That's exactly what this magnitude of alpha is. Okay? And this is then the Hamiltonian that we're really going to sort of focus on. Okay? All right, so we've gone into a rotating frame, we've made this displacement transformation. I've given you a justification to make the Hamiltonian easier and to throw away this nonlinear piece. The question now is, well, you're left with a quadratic Hamiltonian. Is that really interesting? Right? A quadratic Hamiltonian, that's something that we could all diagonalize in terms of normal modes. It's a bunch of harmonic oscillators. Why is this still interesting? Well, the interesting thing is, look, I still have an interaction between phonons and photons, and I have a tunable interaction strip. Okay, more than that, with this basic interaction, if I also think about playing around with this detuning, right, this delta here, and I imagine the mechanical frequency is large, well, I can actually do some fun things with this Hamiltonian. And so I'm going to make use of the rotating wave approximation that Steve told us about earlier. So imagine I actually pick a detuning where this delta is equal to the negative of the mechanical frequency. So in that case, it's like the phonons and the photons are resonant with one another. The rotating wave approximation basically means only keep the terms in the interaction that conserve energy. So if these guys each have the same energy, if I destroy a photon, I better create a photon. So what I get in terms of an interaction Hamiltonian is this so-called beam splitter or swap interaction. Right? So an interaction that turns a photon into a phonon or vice versa. So that's an interesting thing to have for lots of reasons. As we'll see, this is a nice thing to have if you want to cool the mechanical resonator. This is also a nice thing to have if you wanted to take some interesting quantum state in the cavity and put it into the mechanical resonator. Right? Because that's exactly the kind of interaction that moves things from the photons to the phonons. Okay, well, look, you could do something else. How about we pick a different frequency for the drive on the cavity? So I pick this detuning, the frequency of my laser, to be bigger than the cavity frequency, this detuning to be plus the mechanical frequency. So now this is omega m, this is minus omega m. The terms that conserve energy in this interaction either involve creating a phonon and a photon or destroying both of them. Okay, so in this regime, if I make the rotating wave approximation, I end up with this Hamiltonian, which doesn't conserve the number of excitations. So this is the interaction that we'd associate with a parametric amplifier. It's the kind of interaction that will give us entanglement. Okay, and how do I see that? Well, imagine I start with no phonons and no photons, and I turn on this Hamiltonian. What is this going to do? It's going to start creating phonons and photons, right? But what's the nice thing? There's going to be a complete correlation. Every time I get a photon, I always get a phonon. So turning on this Hamiltonian, it's creating these correlated pairs of phonons and photons. That will be a route to entanglement. Okay, so the upshot of all of this, even though we've ended up with a quadratic Hamiltonian, there's still going to be a lot of nice things we can do with this system. Okay, let me just quickly pause. Everyone still on board? Everything making sense? One other thing I should sort of warn you, in putting together this talk, I've taken slides from a lot of different places, and in some cases from different people. And so what that means is there's an unwanted kind of noise in this talk, notational fluctuations. So if you notice a symbol that just appeared out of nowhere and isn't defined, please ask, okay? Because that's definitely a mistake that I've made. All right, so we have this linearized Hamiltonian. I should quickly point out, even though I'm not going to talk about this nasty and interesting, truly nonlinear term, I think it's going to be mentioned in Peter Rabel's lectures. Maybe if you ask him nicely, he can tell you about that. And also my student, Marc-Antoine, will hopefully have a poster where he'll discuss some work we've been doing. Also, trying to understand what that term there does. Okay, but that's the last I'm going to say about it for now. Okay, so we have this coupled system. We've talked about these different transformations we can make. Where should we go next? Well, let's just try to understand what the basic consequences of this coupling is. Okay? And the simplest way to approach things to begin with is to take a semi-classical point of view. So what does that mean? Well, look, we have the Hamiltonian. We have this Hamiltonian. We could write down the Heisenberg equations of motion. Those are operator equations. I don't like operators. Let's just take average values of everything. And let's further assume that the average value of a product is the same thing as the product of average values. So then all our operators just become numbers. A, that lowering operator, becomes a complex number alpha. Okay? Mechanical position, which was B plus B dagger, now is just position like it would be classically. So we can basically get the semi-classical equations of motion for our system. So these equations are in that rotating frame where the laser is time independent. I'm keeping the full nonlinearity in the system though now. I'm not making this displacement transformation. So here's the equation of motion for the cavity. Here's the laser detuning. This is the optomechanical interaction. This is the derivative of the cavity frequency with respect to position. Okay, so this is telling me, hey, look, the frequency of the cavity depends on position. This is the damping term, and this is the laser driving. Okay, so that's the cavity equation of motion. In terms of the mechanical resonator, right, well, here's the restoring force of the oscillator, it's spring constant force. Here's the mechanical damping, right? The mechanics 2 will lose energy, and the damping rate I've written is little gamma. And this is that radiation pressure force. Okay, the fact that if I have photons in the cavity, that's a force in the mechanics. Okay, yeah?
Did you say that this was like, we now return to like a completely like nonlinear description?
Yeah, so I haven't dropped anything in the coupling. What I've done is I've made the system completely classical. I'm dropping any kind of noise in these equations.
Oh, but
yeah.
So I still think it's linear because you only use omega prime, like the omega d.
Okay, so we've got to be careful. So yeah, there are different things that we could linearize.
Oh.
So what I have linearized is in the basic Hamiltonian, I'm only going to worry about the cavity frequency depending on x.
Okay, and that's still linear.
But then there was an additional linearization that I talked about, right? Even if I do that, I still have a nonlinear term like this.
Oh, okay.
And that I'm still going to keep. Yeah. Okay, so even just looking at these equations, how do I see that they're nonlinear? Right, on the right-hand side, I have terms that aren't just linear in x or linear in alpha. This is a nonlinear term. It's quadratic, x times alpha. That's alpha squared. That's also nonlinear. Okay, so we got these coupled equations. They're classical. They have no noise. It looks like this is pretty innocuous. So what's going to happen? What should we start to look for, right? Well, the simplest thing to look for is just what are the stationary solutions, right? So look, if there was no coupling to the mechanics, I know that if I drive the cavity with some laser light, I get some average amplitude alpha L. And now I couple the cavity to the mechanics, how do things change? So let's just solve for the stationary state of these equations. That's pretty easy. So I set a 0 over here. What do I get? Well, because of this radiation pressure force, the mechanics is going to be displaced at amount alpha squared. So I solve this for the equilibrium position of x. X is proportional to alpha squared. I put that back into the equation of motion that tells me what is the cavity amplitude. And what do I find? Well, here's my equation. I basically find that that term here becomes something that's proportional to alpha squared. Right? This is just saying that x has been displaced at amount modulus alpha squared. So what is that? Well, again, remember the detuning is really the laser frequency minus the cavity frequency. This is basically telling me that because of the interaction with the mechanics, the cavity frequency has become amplitude dependent. It's as though the cavity frequency changes the more photons I have in the cavity. And this is exactly what we would expect, not for a simple harmonic oscillator, but for a nonlinear oscillator. An oscillator with a Kerr-type nonlinearity or a Duffing nonlinearity. Okay, so one basic consequence of this coupling is the cavity, because of the interaction with the mechanics, inherits a nonlinearity. Okay, an effective Kerr or Duffing type nonlinearity. And one thing we hopefully all know about nonlinear oscillators is that if you drive them hard enough, what does a resonance curve look like? It no longer looks like a simple Lorentzian. It can actually fall over. Right? So if I actually ask now for this system, how many photons are in the cavity as a function of the laser detuning, that's the x-axis here, and the different curves here correspond to cranking up the laser power. Cranking up the laser power means increasing the magnitude of this term here. Well, for weak power, I have these nice Lorentzians. For higher power, this curve tilts over. And again, that's just this frequency pulling effect, right? The bigger alpha is, the smaller the cavity frequency is. And why is that interesting? Well, look, for certain values of the detuning, you actually have more than one solution to these classical equations of motion. And that's the basic physics of bistability. That's something that you could see in an experiment by doing a ramp and seeing basically hysteresis. And again, the first evidence of this kind of optomechanically induced bistability, again, goes all the way back to 1983 and is something that Pierre was involved with. Okay, so one basic consequence of this interaction, if I just look at things from the point of view of the cavity gets an effective nonlinearity, a Kerr nonlinearity. And one thing that can give you, if you detune to the red, so detuning that's less than 0, you can get bistability. Right? For a given laser drive, there could be more than one solution for the classical amplitude. Okay, so the interaction changes the property of the cavity. What about the other way around? Right? What happens to the mechanical resonator as a consequence of this interaction? And so what I'm going to tell you about is, people refer to this as dynamical back action. It's a back action anytime the light messes up the mechanics. Call that back action of this system. Dynamical because I'm actually really interested not just in what's the average value of the position, but does this interaction between the mechanics and the cavity field, does it actually change the way the mechanical resonator moves? Okay? So now to address this question, I am going to make that linearization that we made before. Okay, so what I'm going to do with these equations, because again, these equations are nonlinear, I've solved, let's say, the stationary state already, like we did in the last slide. And then I'm going to assume, okay, well now my mechanical resonator is oscillating, it's moving a little bit. So x of t is its stationary value plus some small displacement. And I'm going to write the same thing for the cavity field. The cavity field is its equilibrium value. And again, we always have a laser drive in the problem. Plus some small deviation away from that. Okay, and I'm going to assume the same kind of thing we did before. Look, I'm driving the laser, the cavity strongly. This is pretty big. This term here is really just coming from the optomechanical interaction because x is oscillating. Alpha is actually going to change as well, but the coupling is weak, and this alpha bar is strong. you know, this thing is relatively smaller than this thing. So that means in these nonlinear terms, right, when I plug this in and expand, I only need to keep the terms that have at most 1 delta alpha or 1 delta x. Okay, so it's the standard way we linearize a set of nonlinear equations. Why do we like linear equations? We can solve them exactly. What am I going to do with these equations? Well, I want to know how the motion of the mechanics is changed by the interaction with the light. So let me put an additional term on the right-hand side of the mechanical equation. Let me put a driving force. Right, let me call that an external force, F external of t. And let me now ask, well, how does the mechanical resonator respond to that driving force? Okay, so this is something that algebra we can all do. We make this linearization. I put in the driving force. I basically solve for this delta x of t. Okay, and again, the easiest way to do this is to Fourier transform the equations. What do we find? Well, look, everything is linear now. The delta x of omega, the oscillations of the mechanical resonator, are proportional to that driving force. All this stuff out front, that's what we would call a force susceptibility. In this talk, I'm going to use the notation we like, chi xx. And so what is sitting here? Well, first of all, if there was no optomechanical interaction, we could ignore this sigma here. This is just the force response of a damped harmonic oscillator. Right, so I should have included the plot here. This just has 2 Lorentzian peaks at the oscillator resonance frequency, right, omega m. And again, here's that notational noise I told you about. The damping rate of the mechanical resonator has become a big gamma here. Okay, so without the sigma, this is something that you hopefully all know and love. It's just the force response of a damped harmonic oscillator. Because of the interaction with the cavity, this force response is changed. And all of that change I've lumped into some function here, sigma of omega. Okay, now what's the idea? Well, again, this thing is going to be small. It's going to be proportional to the optomechanical interaction squared. Okay? And so the idea is, well, look, where is the susceptibility going to be large? Right? At what frequency do I have to drive the mechanics to get a big response? Well, on resonance. So really, all I care about this function is what does it do right at the mechanical resonance frequency. Okay, so whatever this function is, I'm calling it a self-energy function. Right? It will have a real part and an imaginary part. So how am I going to interpret the real and imaginary parts of that? Well, the real part of this, let's just go through this. Well, this term here is real. The real part of this I can interpret as a change in the mechanical frequency. Okay, the imaginary part of this, well, what else is imaginary here? It's the damping rate. So the imaginary part of this I could interpret as a change or an additional damping term for the mechanical resonator. Okay, and so this is the basic idea of these dynamical back-action effects. Because of the interaction with the light in the cavity, there's a change in the mechanical frequency, and this is known as the optical spring effect. It's like there's a new spring constant in the problem that's coming from the light. And there's also a new damping rate in the problem, and this is known as optical damping. Okay? And it's nice to have just a kind of very equation-free, even more semi-classical interpretation for this. Right? So imagine I slowly sweep the mechanical position. By hand, I drag that mirror, increase the length of the cavity, and I actually ask what happens to the photon number in the cavity. Well, as I change x, right, I'm changing the frequency of the cavity. I'm going to take the cavity through resonance, right, with the laser. So that's what this blue curve here is, right? It's just the cavity resonance. And again, in our system, the number of photons in the cavity is the same thing as the force of the mechanical resonator. So as opposed to labeling this with n, I've labeled it with f. So this blue curve is if I did things infinitely slowly, right? I'm just going to trace out the resonance of my cavity. But now if I actually sweep the cavity, the mechanical resonator, change its position at some finite rate, the cavity won't be able to perfectly keep up with the change in its frequency, right? I change the frequency of the cavity. It's going to take time for some extra photons to come in or some photons to leave. So what I'll actually find is for a finite sweep rate, how does the photon number change with x or with time? There's going to be a lag compared to the case where I did things infinitely slowly. So one equation to describe that, the change in the cavity photon number due to this motion of the mechanical resonator, it's not going to be strictly proportional to x. It's going to be proportional to x at some slightly earlier time. Because of this lag time, it takes time for photons to come in or out of the cavity. And so that lag time is sufficiently small, I could just Taylor expand that. So the change in the cavity photon number due to the mechanical motion, right, has a piece that's proportional to x and a piece that's proportional to x dot. But again, cavity photon number is a force, right? So this are two terms in the radiation pressure force on the mechanical resonator. Well, the force that's proportional to x, that's just a spring constant. That's the optical spring we discussed. And a force that's proportional to x dot, that's a damping term. Okay, so that's another way of understanding what you'll generically get out of just solving these equations, right? Why you actually get both an optical spring and a damping force. And again, the interesting thing is, if you look at the sign of these effects, there's another way of looking at it. Here again is this, force versus mechanical position curve. If the oscillator is oscillating, right, I'm just going back and forth, right, I'm actually going to form a loop in this curve, right? Because again, the force, the number of photons in the cavity, doesn't follow the mechanical resonator perfectly. So if I have an F versus X, plane, and I have a curve that forms some area, the area in that, that's enclosed is going to represent work. Okay, and one thing that you can just see by looking at the signs here, depending on the detuning of the cavity, whether I do the loop out here or loop out here, the sign is actually different. In this case here, I actually find that I'm doing negative work on the oscillator. I'm taking energy out of the oscillator. That's damping. That's what we would naively expect from these kinds of arguments. On the other side out here, I'm actually doing work on the mechanical resonator. I'm putting energy into it. And so one thing that can actually happen from this kind of physics is you can get anti-damping. Okay, the optical damping can actually be negative. Okay, and it's nice to point out that even though these ideas have had a real renaissance just in the last few years, the basic idea is that, look, this could happen in this kind of cavity optomechanical system. Really go back to pioneering works by Brzezinski in the late 60s, trying to understand the physics of interferometers. Okay, so let's go back to this, all the qualitative way of understanding this. If I go back to these equations, there was this self-energy function that told us what was happening. It turns out in this system, it's very easy to get an exact expression for this. Okay? So this self-energy, the real part is this change in frequency, imaginary part, damping. It's really just the sum of two Lorentzians. Okay? And so again, all these slides will be up so you can look at the equations in more detail. So if I actually make plots of what's going on, right? So let's actually ask, how big is this new damping rate from the mechanics? How big is this change in frequency? If I pick a mechanical frequency that is smaller than the damping rate of the cavity, well then these Lorentzians are going to be pretty smeared out, because again the damping rate is bigger than the actual location of the resonance. And so the damping rate is two very weak, highly damped Lorentzians. The change in frequency, derivative of Lorentzians. If you now reduce the damping rate or increase the mechanical frequency, well then you see that, look, these damping rates have these two big peaks in it, and the mechanical frequency has this nice structure to it. Okay, so all of this just comes from those simple equations. So again, from these interactions, we have a frequency shift of the mechanics. We have some extra damping. Okay, the motion of the mechanics is going to be changed by the interaction with light. So what? Well, let's really focus on this damping rate curve. On the left-hand side here, where we actually get a whole lot of extra positive damping from the light, that's actually going to be a route to actually getting cooling. And this is going to be a way to actually, eventually cool the mechanical resonator all the way to the ground state. On the other side here, this is where we get this anti-damping. Through this interaction, work is actually done on the mechanical resonator. This is where we could say we get heating, where you can actually get a kind of instability. Okay, so let me just briefly tell you what happens on this heating side. This is when you pick a laser detuning that's positive, which means your laser frequency is bigger than the cavity frequency. Okay, and so what's going to happen? Well, so we're sitting out here, right? We're doing a loop out here as the oscillator oscillates. Work is being done on the oscillator. So even if the oscillator starts not doing a whole lot, right? Because I have negative damping, that means, positive damping, the amplitude would decay exponentially with time. Negative damping, the amplitude will grow exponentially with time. So as time goes on, the oscillations will get bigger and bigger and bigger. Does that go on forever? No. What happens? Well, the approximations that we've made are going to completely break down. Right? So I said, look, we're going to linearize the equations of motion to describe these effects. Because of this instability physics, right, the oscillator is going to start having a very large amplitude of oscillation. Even if I have a weak coupling to the cavity, I'm going to get to a regime where the oscillator is oscillating so much, it's going to strongly affect what the cavity is doing. Okay, so what you have to do is you have to take these semi-classical equations seriously. You have to solve them, including all the nonlinearity. And so what's shown here is a plot taken from the work from Florian Marquardt's group. And what's being plotted here is basically how much power is being dumped into the mechanics from the cavity. And on the x-axis here is that detuning parameter. And again, for negative detunings, that's where we expect this instability physics is negative damping. Everything we talked about before was for very small amplitudes of mechanical motion. And so now the amplitude of mechanical motion is this y-axis here. Okay, so the idea is, out here, you actually, if I pick some detuning here, I have a huge amount of negative damping. A ton of power is being dumped into the mechanical resonator. What happens? Well, its amplitude increases, which means I need to move down the y-axis. And eventually, as I do that, this negative damping effect decreases. Because now the mechanical resonator is strongly affecting what's going on in the cavity. And eventually, I reach a point where this energy that's being dumped into the cavity, into the mechanics from the cavity photons, is completely balanced by just the intrinsic damping of the mechanical resonator. And that determines that final oscillation amplitude. Okay, so one of the interesting things, and there's lots of interesting things about this instability side, this diagram where you have negative damping, even if you start with a weak coupling, the system is pushed into a regime where the coupling is effectively strong. The cavity is strongly influenced by the mechanics, and vice versa. Okay, so that's the instability side. So let's at least start to say something about the cooling stuff, and I won't go on for too much longer, because I think you do want to get to lunch. So the cooling side, we pick a laser detuning that again is negative, so the damping that's coming from the cavity is positive. Why would positive damping actually give us cooling? Okay, and so to think about that, let's just go back to some things that we hopefully know about, just classically, about a dissipative harmonic oscillator. So classically, how would let's forget about the optomechanical interaction. How do I describe a damped harmonic oscillator? Well, the natural thing to do would be to write down a Langevin equation. So here's my F equals ma equation. Here's the restoring force. Here's a generalized damping force on the mechanics. The mechanical resonator is going to have all sorts of intrinsic sources of damping that will cause this kind of viscous damping force. And then to be in thermal equilibrium, right? To be in thermal equilibrium, I know equipartition must hold that, look, if I take the time average of x squared, that's going to give me something proportional to temperature. Well, if I only had a damping force, x would be 0. Right? So to counteract that damping force, I need some random thermal force fluctuations. And to ensure that I'm in equilibrium, right, so this delta F is random thermal force noise. to make sure I'm in thermal equilibrium, these thermal force noise fluctuations have to have exactly the right size. And that exact right size is basically classically the damping rate times temperature. This is just the fluctuation dissipation theorem. Okay, so this is how I understand the mechanical resonator being at some temperature. There's this delicate balance between these thermal force fluctuations and damping. And the balance between those gives me a temperature. So now, what is it that I hope that I'm doing? When we turn on this interaction with the cavity, we get this extra optical damping. What I hope I'm doing is I'm just increasing the damping term in this equation. So the damping now gets this extra optical damping we talked about. And if I could do that without increasing these force fluctuations, well, then I play exactly the same game. The damping has gone up, the force fluctuations are the same, the temperature would go down, right? And the cooling factor would be the ratio of the old damping, without the cavity there, to the new damping, including the cavity. Okay, so this is the basic, or one basic way of understanding why would this extra damping actually give you cooling, right? It's cranking up a way to lose energy without giving you a way to put more energy in. But of course, a big question now is, well, wait a second. In deriving that result for the optical damping, these semi-classical equations, we made lots of approximations. We threw away all the noise terms in the equations. Right? Everything was classical, so there was no quantum noise. There was no thermal noise. How do I really know that with this optical damping, there isn't an extra fluctuating force noise that I should put there? And if I include that, am I still going to get such a simple answer for this? Okay, so the thing we really have to do to really understand, can you use this optical damping as a way to cool all the way to the ground state, is we have to do a quantum treatment that will really tell us what, if any, are the extra force fluctuations associated with that optical damping. Okay. So in many ways, if we do that, the most straightforward way would maybe be to just write down the full Heisenberg-Langevin equations for our system, linearize everything, so that means it's a set of equations we could solve, and you could basically invert a 4x4 matrix and get the answer. But that's not so exciting or glamorous, so I'm going to take another route to try to understand this cooling physics. And this is the so-called quantum noise approach. And what's nice about this is an approach that is general enough that you can actually use it in other systems where this idea of just solving the Langevin equations isn't going to be possible. Okay, so what's the idea of this quantum noise approach? Here's our basic system again. The way we're going to approach this is we're going to think of the photons in the cavity as another dissipative bath that's interacting with the mechanical resonator. And the way that I'm going to treat the cavity photon as a dissipative bath, well, it's exactly the same way I would treat any dissipative bath, classically. I want to derive what's the damping effect of that bath and what are the force fluctuations. Okay, so in this case here, what's the force exerted by the bath? Well, it's the same Hamiltonian as always. It's just the number of photons in the cavity. And so how do I think about some fluctuating force? So now the number of photons in the cavity is something that's going to have noise in it. It's going to fluctuate. Well, the way that we think about force fluctuations, or fluctuations in general, are in terms of these noise spectral densities. Okay, so here's some noise. Delta F as a function of time has zero mean. It's fluctuating. You couldn't stop me from Fourier transforming that signal. So delta F of omega, the Fourier transform of that would also be some random complex variable. So the force noise spectral density would be, take the modulus squared of that quantity, right? So we get rid of the phase information, and then average that over different realizations of that noise. So this force noise spectral density, it's really telling me how big is the noise at a given frequency. Okay, and that is completely equivalent to this definition here, where you Fourier transform the autocorrelation function of the noise. Okay, that's all completely classical. So in our problem, F is the number of photons in the cavity. The number of photons in the cavity is not completely classical. Okay, so can we play the same games with a force that is constant? Well, You could just copy the same definition for a spectral density, right? So again, I have two force operators. In this case, these are photon number operators. I need to have them time dependent, so they're in the Heisenberg picture. I can take that expectation value, right? So that looks like a very sensible way to think about a noise spectral density, quantum mechanically. What's the problem with this? F of t and f of 0 don't commute at different times. Okay, what does that mean? It means this average value here doesn't have to be real. Classically, of course, it would have to be real, not a correlation function like that. So what does that mean in terms of this spectral density? Positive and negative frequencies are not the same. Okay, so that actually has some physical content, right? That's something that's not true for classical noise. How do we understand what that means? Well, let's just take this definition here, and let's just write out what would this SF of omega be in terms of the unknown density matrix of our bath. The bath here is the cavity photons, and its unknown energy eigenstates. Okay, so I could just take this expression here. These are Heisenberg picture operators. Just expand out that average value. I'll get an expression here that hopefully looks familiar. So rho here is whatever the density matrix of my bath is. I and F are labeling energy eigenstates of the bath, whatever those happen to be. And so what do we see? The quantum noise spectral density at a given frequency basically looks like a Fermi's golden rule transition rate. And the noise at a given frequency corresponds to a transition rate where the change in energy is equal to that frequency. So if we're talking about positive frequencies, we're talking about the initial bath state having a lower energy than the final state. So we're talking about our bath being able to absorb energy. If we're talking about negative frequencies, we're talking about the opposite thing, the ability of the bath to emit energy. Okay, so no matter what the system is that's acting as some kind of dissipative bath, the quantum system, I can always calculate this kind of force quantum noise spectral density. And what that tells me is it really does tell me about the ability of that system to absorb or emit energy. Okay, and so once we do that, again, the big question we're really after, let's go back to the cooling problem. Right, the big question we're after is, well, is there an extra force noise here that goes along with that optical damping? That's the same thing as asking how hot are the cavity photons. Right, to say that the cavity photons give me damping but don't give me any noise, that's like saying there's zero temperature. Right? Classically, that's how you get damping with no noise. So the thing we're after is these cavity photons, how hot are they? And this quantum noise picture gives us a way of doing that. Just for the interest of time, I'll do this a little bit quickly. So basically, the negative noise tells me about the bath's ability to emit energy. The positive noise tells me about its ability to absorb energy. In thermal equilibrium, those would have to be, the ratio would have to be given by a Boltzmann factor, where T really is the physical temperature of the bath. Okay? In general, our cavity photons are not going to be in thermal equilibrium. I'm driving the system with the laser. I can still use this as a way to define the effective temperature of the cavity photons. Okay? So even though the bath is not in thermal equilibrium, this gives me a way of thinking about temperature. What's the price I pay for not being in thermal equilibrium? Well, in principle, I'm going to get a different temperature from this definition for different choices of frequency here. Okay, so we wanted to know how hot are the cavity photons. We need to know that to really understand whether we can cool or not. This quantum noise approach gives me a route to getting that. It's going to give me a temperature that's frequency dependent. I still would like to connect this to that kind of Langevin equation picture we had. Just skip that. And we can do that. Okay, so there's a rigorous way of, in the quantum mechanical sense, of again deriving a classical looking Langevin equation, where now the damping term and this force noise term are really just determined by that quantum noise spectral density we talked about. So the difference between the positive and negative frequency noise, this is telling me that the bath's net ability to absorb energy, that's going to be the damping rate. this force noise term, right? How big is the spectral density of this classical noise term here? I'm just going to take the symmetric part of that noise there, that quantum noise. And so again, the problem is, well, what frequency do I take here? Well, I have a mechanical resonator that has a very high quality factor. There's only one frequency that matters. That's the mechanical resonance frequency. So all I need to know is these quantum noise spectral densities evaluated at omega equals plus or minus the mechanical frequency. Okay, so this is a really generic way of understanding. I take my harmonic oscillator, I couple it to some other interesting quantum system that acts as a dissipative environment. How hot does it look to the mechanical resonator? Calculate these quantum noise quantities. Okay, and so just really quickly to sort of end before lunch, so let's just quickly apply this to this system here. In our case, this force noise spectral density is the cavity photon number fluctuations. I want to know this spectral density, so I need to know the autocorrelation function of the fluctuating part of A dagger A. Well, in this displacement picture, that fluctuating part just involves these D operators, and that's very, very easy to solve. So that's going to be proportional to the average number of photons in the system. It's going to damp away to rate kappa over 2, and it's going to oscillate at this detuning, this frequency that shows up in the rotating frame. So what do we find? This force noise spectral density has this very simple Lorentzian form. So now, how hot are the cavity photons? Well, what I have to do is really compare the force noise at plus the mechanical frequency and minus the mechanical frequency. So here, imagine my mechanical frequency is 1 in these units. So at the positive frequency, I have this nice peak that's sitting here. At the negative frequency, I don't have exactly 0. I still have something. It's the ratio of this to this, these two force noise spectral densities, that will determine the temperature. Okay, and so we can consider just two quick limits. Imagine first that the mechanical frequency is much, much smaller than the cavity damping rate kappa, than the width of this Lorentzian. So then, whether I compare plus or minus omega, I'm just going to shift myself a little bit on this curve, right? The effective temperature I'm going to get there, expressed as a number of quanta, right, is going to be huge. Why? Because the rate to absorb and emit, they're almost the same. Right? The force noise at plus and minus omega are almost the same. So that is not going to be a good regime to cool. Right? A good regime to cool, the opposite so-called good cavity limit, where the mechanical frequency is much bigger than the damping rate. In that case, if I also pick an optimal detuning, where that detuning is equal to minus the mechanical frequency, what that corresponds to is, let me move this thing, this peak, to sit right at plus the mechanical frequency. So in that case, there's a huge peak for the positive noise. The negative noise is pretty much 0, because this Lorentzian, just think of it as having almost no width. And in that case, this effective temperature can be tiny. So that's the regime where you basically can get cooling almost all the way to the ground state. Okay, and so maybe just as we're running out of time, maybe I'll stop things here. So again, the basic idea for understanding this cavity cooling physics, we know that we get damping, optical damping, from the interaction between the cavity photons and the mechanics. To really understand the cooling completely, we need to understand this physics of what's the effective temperature of the cavity photons. And to address that, we can use this quantum noise approach. And what that tells us is in this good cavity limit, we can really have the cavity photons look very, very cold to the mechanics. Okay, and maybe I will pick up from there with, in the next lecture. So, thanks.
Let's see, there could be waiting.